it's okay. But you just need one because the orientation doesn't change. These are orientable surfaces. Now, the steps that we did already, you guys decided that you want to parameterize this surface using the spherical. It is a sphere, it's the shell of the sphere. Therefore, rho is equal to 1. We decided I really don't need to compute the little n through G sub. These are one of those cases that I'm not going to do this. Don't need that. Why? Because you guys know little n is going to be just cosine theta sine phi. It's the spherical if the magnitude was 1. Magnitude 1 means that there is no rho multiplying it. So technically, little n and the parameterization, so the little n and the parameterizations are the same. You draw a point, origin to a point on the surface, and then that gives you a vector or position vector, parameterization. Then you continue that outward. It's going to be orthogonal to the surface. That said, I still need the magnitude g theta cross g phi, which you guys know it's going to be what? It's going to be rho squared sine phi, but rho is equal to 1. Therefore, rho equal to 1, so rho squared sine phi is just that. All that said, now the next step is to multiply f dot n, then by the magnitude of that, and take the integral. What is f dot n? What is f of g of theta and phi? This is, bless you, this is going to be cosine phi, and then sine theta sine phi, then cosine theta sine phi. Agreed? I'm just replacing this for z, that for y, this for x. Now, f dot little n is going to be what? It's going to be cosine phi times sine phi times cosine theta. By the way, here is another one, cosine phi, sine phi, cosine theta. So I will get 2 cosine theta sine phi, cosine phi. And then also I get sine squared theta sine squared phi. Everybody okay so far? Now the last step is to take the double integral from 0. Do you see this? This is supposed to go in there. 0 to 2 pi, 0 to pi. 2 cosine theta, multiply it by sine phi here, sine squared phi, cosine of phi, plus sine squared theta, sine cubed phi, d theta d phi. And then we compute this. Let's see if I can do something easy. You ready? I'm going to separate the first one as 0 to pi cosine theta d theta, 0 to pi sine squared phi cosine of phi d phi. Agreed? Okay, what is that value? 0. And then let's see what I can do for the second one. For the second one, I will have integral 0 to 2 pi sine squared theta d theta, and 0 to pi sine cube phi d phi. Hold on. Everything is okay, right? Yeah, I think so. So this part is 0. I just need to compute that part. And then I know that this becomes 0 to 2 pi, 1 minus cosine 2 theta divided by 2 d theta. And that one becomes 0 to pi sine of phi 1 minus cosine squared phi d phi. Right? And so this part is, the first part is just, the integral of that is going to be 0, so I will have just pi. And then I have to compute the other part by having u equal to cosine of phi, du equal to negative sine of phi d phi. And then if phi is equal to 0, u is equal to what? 1, phi equal to pi, then u is equal to negative 1. So I will get negative 0 to, 1 to negative 1. These two is going to be du, 1 minus u squared. And then you compute that. And you end up with 4 pi third. We're good? Yeah. So that you have to compute the last piece on your own a little bit, right? The negative sign swap the bounds, basically. Okay, so I want to tell you a trick. Can I tell you a trick right now? Or do you want to wait for the next section? You want to now? Here's the thing. Do you see all these vectors coming out? There is a vector field, and the flux is telling me how many things are getting out, how much things are getting out, right? Do you remember this picture appeared in section 16.1? Do you remember what that was? What was that? It starts with D, ends with, ends. What's that? Divergence, right? You're saying things are getting out of this surface. But how do things get out of the surface? There has to be a source within the surface, in the volume of the surface, for the vector field to create things that comes out. What is the divergence of this field? So I'm doing that dot product. The divergence is 1. There is a divergence theorem. Did you see how much work I did? Divergence theorem says compute the divergence and do a triple integral of the divergence on the volume, and it gives you this. Shall I write it down? Is that the divergence? So I'm saying this by divergence theorem. This is equal to the triple integral of divergence of f dv on the inside the ball. inside the sphere. Divergence is 1. Can I bring it out? What would this be? Volume of the sphere. Can anybody tell me what's the volume of the sphere? 4 pi third of r cubed. That is 4 pi third. So all this shenanigan is actually equal to that. Do you see that? It's one line. You just have to know what theorem to use to make your life easier. That's about it. So the next time I'm doing something, let me know if you can come up with a theorem. So I talk about flux. One way to describe flux is, one way to actually, in this course, we do not talk about time. But literally, Calc 3 is frozen in time of whatever you're studying in the next course, right? Because we can bring in entire theorems and bring in the time component of it. So what we do is we say, oh, the vector field is really speed. But we're just frozen in if the speed at that instant. So you don't see it over time. It's changing over time. But we just give you a picture at one instant. We freeze the time, and we give you a picture of the vector field. Fair game? The next course does that. Time is changing and vector field is changing. So what is happening if I consider F, the vector field, to be the velocity of the object, in a small object, right? Let me tell you, velocity, what is the units of velocity? Distance, units of distance divided by time. When I'm doing the surface integral, I'm going f dot ds. What are the units of ds? ds is a surface element, right? So what is that? Distance squared, units of distance squared. Now, when I'm doing the double integral, what is that units now? Distance cubed divided by time. What quantity has distance cubed? Length times length times length is volume. So you're really finding the speed that the volume is going through the surface. So this is volume per time. So when we talk about flux, if you imagine F is the velocity of particle, that's what I wanted to say, not object, particle. When you think about flux as the velocity of the particle, vector field as the velocity vector field of the particle, what you're computing with flux is how much volume is going through, the speed of the volume through the surface. Fair game? From one direction. It tells you about the speed of the volume through the surface. And so the picture is nice, but I don't draw it very well. I did it once, but I sort of used the book's notation. So it's really the book's picture, not mine. But it tells you what you find. You find in the direction, normal direction, and it tells you about the volume that goes through that surface per time, basically. It tells you about that. Now, let's do one eye clicker to give you a quick minute. And then we do one more problem. I do the divergence theorem again on that problem. Okay. So which formula are you planning to use for this? F dot capital N or F dot little n? Little n? Let's do F little n. So if I do F dot little n, right, then I have to have ds as in it's not, let's think about this. So I'm going to do ds as in what's that called? Surface element. Wait. This integral, the double integral and the surface element, if I put a positive value in here, what would the output be? Positive. If I put in a negative value in here, what would the output be? Negative. So the entire surface integral depends on f dot n. What is n in here? What's the orientation? In the z direction, right? Negative z direction. 0, 0, negative 1. Is that a unit vector? Correct. So that's n. And I want to look at this picture. What is on this picture? Can x and y be negative? No. X and y are both positive. How about z? What's the value of z on this picture? Z is equal to 0. Now, tell me, which one of these give you f dot n is going to be, which one of these vector field? So A is going to be 0, 0, and a negative value. Dotted with a negative value, negative 1, it becomes a positive value. So the A dot n, let's see, A dot n is what? Y. What is B dot n? What is C dot n? What is D dot n? Which one of them is negative? Okay, 4, 3, 2, 1, 0. What just happened? Seriously. Which one of these is negative? Oh yeah, I asked for a positive flux. Okay, 4. No, sorry, started. It says positive flux, not negative. Which one has positive flux? That's the one. 4, positive flux, negative z direction. I saw both of them negative. 4, 3, 2, 1. Are we done? 0. Still doesn't work. Okay, so I want to talk about this problem now. So it tells me find the flux out the surface. Can you guys tell me how many pieces this surface has? How many smooth pieces? 2 smooth pieces. So let's see. I have a nicer on GeoGebra, if it comes. Can you guys tell that there is a disk here? And the disk, outward direction for the disk, can you guys tell me what's the little n for the disk? Can anybody tell me what's the little n for the disk? 0, 1, 0. 0, 1, 0. Are you expecting for the paraboloid, are you expecting y to be positive or negative? Negative. Can we remember this? So the little n for disk, for paraboloid, for disk, I'm expecting to get 0, 1, 0 as little n. For the paraboloid, I am expecting n dot j to be a negative value. The jth element of n, jth element of n is negative. Agreed? Okay. Now I'm going to compute each one of these pieces. I did that with my due diligence because it gets lost. So, quick question. Is everybody agreeing that we're going to compute 2 surface integral? Ready for that? So, what's the parameterization? Let's start with the paraboloid. What's the parameterization of the paraboloid? That's a paraboloid. You have x squared plus y squared. Typically, what do you do when you see x squared plus y squared? What's that? It's an r squared, but if I parameterize x and z, r cosine and r sine, right? And it's not equal to a constant. Therefore, r is changing. Agreed? It's not equal to constant. So I can write it as r and theta. And I will have for x, r cosine theta. For z, r sine theta. What do I get for y then? Because it's r cosine squared, r sine squared, I get y equal to r squared. Agreed? So r is between what and what? Oh darn, I don't know. I do. Plug in y equal to 1. R is maximum 1 and 0. Theta goes all the way around. So everything. Now, and a lot of you guys are going to make this mistake on achieve. How do I parameterize a disk? I wrote r and theta. Why did I write r and theta? R is changing, right? Look at this. Look at the red. Is r always 1? No, it's changing. So r and theta. So I will have r cosine theta, r sine theta, and what is constant here? Y is constant. And again, r between 0 and 1, theta between 0 and 2 pi. Now let's compute everything. I'm going to do G1 sub r, which is what? So step 1 is what? I'm not 100% sure, so I'm going to, Alex, you're okay? Okay, so I'm going to do the G sub r cross G sub theta. So for the first one, G sub r is cosine theta, 2r sine theta. G1 sub theta is negative r sine theta r squared. Oh, no, not r squared, 0. R cosine theta. So G1 R cross G1 theta is going to be what? 0, oh no, 2R squared cosine theta, then R cosine squared plus R sine squared negative of that is negative R. Then I will have cosine times 0 minus 2R squared sine theta. Let's do the same step for G2. Then G2 sub theta is going to be minus R sine theta 0 R cosine theta. G2 sub R cross G2 sub theta is what? First one is 0. The second one is minus R cosine squared plus minus R sine squared, which is minus R. And then what do I get? 0 again. Now step 3, choose your n. Step 2, n. Is this n in the right direction? Am I getting negative j? I'm getting negative j, so this is correct. How about the n2? Is this the correct direction? For the disk, your little n has positive j. So what do I need to do? Multiply by a negative sign. Step 3, hold on, I need more information here. Step 3, compute f of G1. F of G1 is 0, y is r squared minus r sine theta. F of G2, G2 is here, 0, 1, r sine theta. Now compute step 3, f dot n1 is going to be what? Can anybody tell me what's f dot n1? Minus r squared. No, r cubed. Minus 2r cubed sine squared theta. F dot n2 is r. Okay, now I'm going to integrate. Step 4, integrate from 0. Because the r and theta are the same parameter, the same bounds, I can put the integral only on one of them. 0 to 2 pi, 0 to 1, negative r cubed minus 2r squared sine squared theta minus r d theta dr. And then you guys are going to compute this. And let me tell you, I have to replace sine squared theta with 1 minus cosine 2 theta divided by 2. So 2 sine squared theta is 1 minus cosine 2 theta. Finally, what I get is integral r cubed dr, 0 to 1, 2 minus cosine 2 theta d theta 0 to 2 pi plus, there was a negative sign here, sorry, plus 0 to 1 r dr, 0 to 2 pi d theta. This is going to turn out to be negative 1/2. That is going to be plus 1/2, 0. All that work and I got 0. Okay, so my question is, was this surface closed? Surface was closed. Could I have done the trick that I did with the divergence? What is the divergence of this shape? Divergence of f is equal to partial with respect to x of 0, partial with respect to y of y, plus partial with respect to z of negative z. It's 1 minus 1 equal to 0. Did you see how much work I did? Was that not enough? Was it painful enough for you guys to remember? Divergence 0. So the surface integral, the flux, is just equal to the triple integral of 0 dV on the volume, equal to 0. So I could have done this instead. And sometimes it's not just that. Sometimes as one of these surfaces is very nasty, and then divergence is easy. So you compute that, and then you say, because the sum is equal to the volume, divergence over the volume, I can compute one of them. That's one of the questions on the achieve. Yes, divergence has to be on a closed figure. Divergence theorem is on closed surfaces only. That was the story. Oh, the derivatives have to be continuous, and the surfaces have to be piecewise smooth, orientable, surfaces, and the vector field has continuous derivative. You want divergence to be continuous and nice. Okay. Summary, I'm going to talk about it again later. Let's start another section. Sorry, guys. Okay, so here's another section that I want to talk about. It's called Stokes theorem. What was the Green's theorem? Do we remember Green's theorem? So you had a curl and a double integral, right? You had a curl and a double integral. And the other side was a contour line integral. Same thing here. Curl is actually over a surface that is not flat. That's the only difference. So you will have surface, instead of double integral, you have surface integral. So what's the difference between Stokes and Green's theorem? Stokes and Green's theorem. The difference.
One is surfaces to lines, and the other is volumes to surfaces.
The other way around. So the Stokes theorem, the only difference is that you have surfaces that are not flat. So the double integral in the Green's theorem becomes a surface integral. That's the only difference. So Green's theorem, you remember? Double integral becomes surface integral because surfaces are not flat. So Stokes theorem, first of all, let's see, do we remember the left hand? Yeah, the left. So if I'm walking, I want to say the orientation of the boundary versus the surface has to be this. If I'm walking around the boundary, can you guys tell me the boundary is C1 and C2? Can everybody see that? Boundary is C1 and C2. Right here, right there. If I put my head in the direction of normal, so me and normal are sticking out the same way. Normal doesn't go the other direction of the surface, I'm in this direction. Both of us are in the same direction. If I'm walking on the boundary, and I stick my left hand out, if my left hand is toward the region, then the orientation of the boundary and surface match. If I am doing that and my right hand is toward the region, it's the negative of each other. Time? You guys go. Which one are oriented with this rule? Right? This is actually called right-hand rule. Head is sticking out of the pants. Pants, yes. Pants surface. So head is sticking out of the orientation of the surface is sticking out of the pants. If I'm walking in the C1 direction, is my left hand? I'm walking outside the pants because my head should be in direction of the normal. Is my left hand toward the region or not? C1. I'm walking on top of the pants, like I'm going this way. It's toward this, right? Okay, how about C2? If I'm walking, no. How about C3? Okay, so which ones are oriented according to right-hand rule? Which one is not? Yes. No, left hand to be inside. It's called right-hand rule because you can do it with your right hand also. You assume your right hand is the person. Thumbs goes to the direction of the surface, and then when your fingers are pointing toward the direction of the road, and then your palm should be toward the surface. So the fingers are supposed to be going the direction of the boundary, thumb toward the region, and then your palm should be toward the surface. What is the answer? What is happening? One, my left hand is toward. Two, my right hand is toward. Three, my left hand is toward. So right hand rule is the left hand. The one that we had most. D is the answer. 4, 3. Yes, D. I'm dead. 4, 3, 2, 1. 0. Are we good? Okay. So what does the Stokes theorem say? If a surface is smooth or piecewise smooth, and boundary is simple, if orientation is the right-hand rule, orientation, then you guys know this punchline. What is the contour integral? F dot dr. Over here I have a double integral. I will have a curl of f, not the z component anymore. I go ds instead. And so this is going to be the surface. That one is going to be the boundary. Fair game? What changed? That part, right? This part only. Fair game? Okay. So here, when you're doing Green's theorem, n is going to be k. So by replacing k in here, you get the Green's theorem. Green's, this one's Stokes. This one is Stokes. Stokes theorem. And then if I want to, Green's theorem is just this in 2D. 2D. It's flat surfaces. Okay, so let me give you an example. Guys, stay with me. Stay. Gavel time? No gavel? No gavel bobble? Okay, so again, Stokes and divergence theorem are going to make your life easier. They are the theorems that make your life easier. When we ask questions, we ask them so you guys actually use them to make your life easier. Because going directly at it is going to be difficult. First thing I do is I verify Stokes theorem for this example. How do I verify Stokes theorem? There are two sides of Stokes theorem. Which one do you want to do first? The surface integral or the line integral? Surface integral first? Okay. So what is the orientation? Orientation is outward, upward. Is my left hand toward the surface if its orientation is upward? Yes? Yeah, it would be. Going this way, I'm cupping it. So now, first, surface integral. So I have to do the surface integral of curl of f dot ds, and so on the surface S, curl of f. What is curl of f? IJK. It's a cross product, right? So when I'm computing it, what do I get? 0, then what? Are we sure? 0. And then what do I get at the last? 1 plus 2y. Okay. Now, what do I need to do next? Well, let's say steps. Step 1, it's a surface integral, right? G of something. What should I choose for G? G is this yellow surface. What's the equation of it? Circle? No, it's actually a disk, but it has an other equation. Take care, guys. Good luck. Watch the rest. So I could do r theta, right? Is r changing? Theta changing? Wait a minute, I only did x and y. How do I find z? Z is equal to 2 minus y. Y is? Okay, I found g. Now I can do g sub r, which is cosine theta, sine theta, negative sine theta, g sub theta, which is negative r sine theta, r cosine theta, and minus r cosine theta. G sub, this is now step 2. G sub r cross g sub theta is what? Minus r sine theta cosine theta plus r sine theta cosine theta. What is that? 0. Now what do I have? Minus r cosine squared theta minus r sine squared theta and negative sign with that. So it would be r. And then what do I have at the end? I have r cosine squared theta plus r sine squared theta r. Agreed? Okay. Now step 3. What is my integrand? What is my integrand? Curl of f. Curl of f is my integrand. So I'm going to dot curl of f dot, oh wait, I skipped this step. You guys can complain. What is step 3? I have to choose n. Is n in the right direction? Well, n is going this way. Is y and z going to be positive or negative? Positive. N is the right direction. And then curl of f dot n. Curl of f is 1 plus 2 r sine theta dot 0, 0, and 1. Dot 0, r, and r, which is going to be 2r squared sine theta plus r. If I integrate this, what do I get? 0 to 2 pi, 0 to what? 0 to 1. Is going to be pi. And verification requires me to do the other part. I'm going to do it on Friday and give a bunch of icebreakers, and then Wednesday. Class on Wednesday. Friday is going to be review day. Sorry, guys. I took longer than I was expecting.